T2 condition in your syllabus. So I'll be talking about the different boundary condition. So first is your specific temperature boundary condition. A specific temperature boundary condition. What do you mean by this? So the temperature is fixed at the temperature is very specific. So let's say you are having this slab. This is at x is equals to 0, at x is equals to L. Here temperature T is equals to T1 and temperature T is equals to T2. So at both left and right face, you see the temperature is fixed. That's why this is called as the specific temperature boundary condition. So here this is at x is equals to 0, temperature T is equals to T1, and at x is equals to L, temperature T is equals to T2. So this is your boundary condition, and this is called as the specific fixed boundary temperature boundary condition. So this was first. Second boundary condition is your specific heat flux boundary condition. Fine. Okay. So a specific heat flux boundary condition. Again, this is a specific heat flux. So heat flux will be constant. So let's say this is a plane slab I'm assuming. This is your x is equals to 0 and this is x equals to L. So here you will be applying a heat flux, and here you will be applying a heat flux that is constant. So at x is equals to 0, Q is equals to Q lab L. There is a heat flux. Q is your heat flux. Fine. So here it is QL and here it is QR. So at x is equals to R, Q is equals to QR. So these two boundary condition are your specific heat flux boundary condition. So in the problem, if it is given at x is equals to 0, heat flux is this one, and at x is equals to L, the heat flux is this one. So you have to understand, okay, this is heat flux boundary condition. But you don't have to remember the name of the topic, that is the specific heat flux boundary condition. But from now onwards, what you need to understand here is that, okay, QL is a heat flux that is being applied at when length is x is equals to 0, that is what left surface, and there is a heat flux that is QR that is being applied at x is equals to L on the right surface. That's it. So now third boundary condition that I'll be talking about is convective flux boundary condition. What is convection? So in previous class I have talked about, again with time I'll be talking about in the subsequent class what is convection and radiation also. But just in order to understand the boundary condition fundamentals, that's why I'm just trying to discuss this thing. So there is a mode of heat conduction, that is conduction, mode of heat transfer, that is conduction, convection, radiation. So if convection is happening, so there may be a different kind of boundary condition also. So just try to understand, if this one is a slab, right? So in this slab, conduction will happen. So let's say here temperature is T1 and here temperature is T2. And on the left side, there is a air medium, that is temperature is T infinity 1, and here there is T infinity 2, temperature is T infinity 2. And here there is air, let's say, or any kind of fluid. I'm air. And the heat transfer coefficient is H1. And again here, this side also, there is air or some kind of fluid surrounded by it. And here also the heat transfer coefficient is H2, right? So if I want to write the heat flux over here or a boundary condition over here, so the rate of heat transfer by convection, that will be the rate of heat transfer by conduction, and again at the this surface also. So if this is at x is equals to 0 and x is equals to L, so what I can write here is at x is equals to 0, the Q by convection, that is equals to Q by conduction. So Q by convection is equals to what? H into this surface area will be there here, A into T infinity 1 minus T1, right? That is equals to minus Ka, what? dt by dx at x is equals to 0. So this is rate of heat transfer by conduction. This is rate of heat transfer by convection. So in subsequent lecture, I'll be talking about the rate of heat transfer by convection. So this is called as the rate of transfer by convection, that is equals to rate of transfer by conduction. So this is your first boundary condition. In this second boundary condition, if I am assuming A and B, so at x is equals to L also, what is happening? Rate of heat transfer by conduction is equals to convection. So I can write minus Ka dt by dx at x equals to L, that is equals to what? H A T2 minus T infinity. Is it clear? So this is the convective rate of heat transfer by conduction transfer by conduction at right phase, that is equals to by convection in surrounding fluid. Is there any doubt till now? Everything is clear? Okay, so now I'll be talking about the fourth boundary condition, that is the interface boundary condition. Right. So what do you mean by interface? Just try to understand. If we have two slabs, let's say, if this one is a red slab and this one is a blue slab. So if temperature here is T1, here temperature is T2. So both of these slab are different. So here temperature thermal conductivity is K1 and here thermal conductivity is K2. So both of these slab are connected together, but due to temperature difference, since I am telling you here temperature is more and here temperature is less, so heat transfer will start taking place from left side to right side, from T1 side to T2 side. Fine. So definitely at this interface here, you can see there will be what? Rate of heat transfer by conduction from first fluid, first slab, that is equal to rate of heat transfer by conduction from to the second slab. And if I am assuming at x is equal to 0, if it is at x is equal to plus L, and if it is at x is equal to minus L, so can I write minus K1 A del A1 del T by del x at x is equals to 0, that is equals to minus K2 A2 del T by del x. So if I am assuming A1 equals to A2 equals to A, so what will happen? The area will get cancelled out. So finally you will be getting K1 del T by del x at x is equals to 0, that is equals to minus K2 del T by del x at x equals to 0. So again this will get cancelled out. So that is K1 del T by del x at x is equals to 0, that is equals to K2 del T by del x at x is equals to 0. So finally you will get this kind of derivations, something like that. So they can ask you which kind of, I mean, they will frame a question in such a way that they will be asking you about which of the following options are correct about this boundary condition. So you need to understand, okay, two slabs are connected with each other, then this kind of boundary condition will be feasible. If there are surrounding fluids, then convective heat transfer is equal to conductive heat transfer, boundary condition will be feasible, something like that. Okay. Yeah, interfacial boundary condition is same as the composite wall, right? Okay, yeah. So due to the interfacial boundary condition, only the concept of this composite wall came. So in future, in the next class, I'll be talking about the when I will be talking about the problem on the composite wall. So there you will know, you'll get to know about that how the problem or how the temperature variations inside a composite wall came due to this particular boundary condition. So first you will understand the boundary condition, and based on the boundary condition, you will apply the boundary condition, and after that you can categorize the problem in the different frames. So this is a concept, and composite wall is a problem. So obviously, both of these are connected with each other, right? Okay. So just try to understand one thing. So we are having two slabs connected with each other, having thermal conductivity K1, K2. Heat is flowing from here. Let's say Q. This is Q dot is rate of heat transfer. And if temperature here is T1, here temperature is T2, and here temperature is T. Here x is equals to 0, x is equals to minus L, and x is equals to plus L. So what will happen over here? So the heat which is going here, it will go and it will come here and it will be coming out. So can I say that Q1 equals to Q2? Can I say minus K1A if I am assuming area A1 equals to A2 equals to A dt by dx in slab first, that is equals to minus K2A dt by dx in slab second. Is it clear? And what is dt by dx? Slope of temperature versus x curve. Fine. Since area is same, so it will get cancelled out. So you are getting K1 dt by dx in 1, that is equals to K2 dt by dx in second. So I am just writing K1 multiplied with slope in first slab, that is equals to K2 multiplied with slope in second slab. So once you multiply with constant thermal conductivity with slope, then it will be equals to thermal conductivity into slope. So if I am assuming, let's say K1 is greater than K2, first case. If K1 is greater than K2, what will happen? If this is greater than this one, so that definitely this should be less than this one. Let's say if x multiplied with y equals to p multiplied with q. Fine. So let's say I'm assuming x is 4 multiplied with let's say 4. that is equals to let's say 2 multiplied with 8. Fine. So here what do you see? X is greater than P. Fine. But let's say I'll decrease X is if X into Y is equals to P into Q. So what will happen? If X is greater than P, then Y will be less than Q, definitely. So here, if this one is greater than this, then this should be less than this. So what will happen for if K1 is greater than if K1 is greater than K2, then what will happen? Slope 1 is less than slope 2. Is it clear? Is there any doubt in this? Okay. So what I can say that del T by del X in 1 is less than del T by del X in 2. So sometimes they will ask you this kind of problem. Here temperature T1, T2. This one is slab 1, this one is slab 2, having thermal conductivity K1 and K2, and they will give you this kind of plot. So they can ask you option A, K1 is greater than K2, option B, K1 is less than K2, option C, K1 equals to K2, and option D, none of these. So just tell me which of the following options will be correct. No, no, no. Here from the curve, you can see that this is slope and this is slope. So which slope is more? I have given you just the opposite question. So here from the curve, you can see this is slope and this is slope. So obviously here you can see slope for first is greater than slope for second. So you are let's say you have two straight line. One is like that and one is like that. So which having slope is more? This one is having more slope. This one is having less slope. So if slope 1 is greater than slope 2, so what will happen? K1 will be less than K2. Is it clear? So these kind of questions you may be asked in the examination. So you have to understand this kind of things, right? So it may be possible this kind of questions may be there, having K1, having K2. Option B, again this is K1 and K2. The option C is here K1 and K2. So just tell me about all of these question A, question B, A, B, and C. So what is the relation between K1 and K2 in A, B, and C? All tell me. What about question B? I have given you three, A, B, and C. So in B, what? Yeah, good. K1 is equals to K2 for B, and here in this problem, K1, since slope in K2 is more, so K1 is greater than K2. Here K1 equals to K2, and here slope is more, slope is less. So what happened? K1 is less than K2. And so this was some kind of boundary condition. I hope this is clear to all of you now. Is there any doubt till now? Okay. So now the fourth boundary condition, that is called as the symmetric boundary condition. So what is symmetric boundary condition? So let's say we are having the slab. So if temperature here is T is equals to T1 and here temperature is equals to T equals to T1. So that is called as the symmetrical boundary condition. So in symmetric boundary condition, what you will see? So let's say this is at x is equals to minus L. X is equals to minus L, x is equals to plus L. So when at x is equals to 0, what you will see, the since this is a symmetrical boundary condition, so this will be like that. The slope will be 0 at x is equals to 0. So at x is equals to 0, yeah, slope dt by dx is equals to 0 due to symmetricity, right? Why? Because here also the slope you will see this will go like that, and here also it will go like that. So because due to the symmetric boundary condition only, so the thing that is happening in the left side, that will be equal to the things that is happening in the right side. So that's why the temperature slope will be 0 at x is equals to 0 over here. Right? And the next boundary condition that I'll be talking fifth one is your insulating boundary condition. So that is insulated boundary condition that says you that if there is a slab over here, if this is x and this is temperature, so if x is equals to 0 and x is equals to L is here, so if there is an insulation here, so there won't be any heat flow, right? So so I can write at x is equals to 0, q dot is equals to 0. And what is q dot? Q dot is equals to minus ka dt by dx, right? So since k cannot be 0, area cannot be 0, so this has to be 0, right? If it is 0, that is equals to minus ka and dt by dx. So it cannot be 0, this cannot be 0, so only this has to be 0. So for insulating boundary condition, only you have to see dt by dx at x is equals to 0, that is equals to 0, or dt by dx, here I am writing at x is equals to 0, that is equals to 0. That is called as the insulated boundary condition.